Experiment 1 had a 64% reaction. The copper 2 here was the limiting reagent. The tin was excess, so we didn't have as much tin react, but the copper, 64% of it reacted. That's the limiting reagent. Normally in the limiting reagent problem, all the limiting reagent is consumed, but in this case, we didn't consume it all. The reason we didn't consume it all is because this is a reversible reaction. And, some can go back up the hill. And so if we use this to predict it, then we go on to experiment 3, we expect it to be in a ratio of 64 to 36%, but it doesn't. It comes out at a different ratio. So if I start off with 100% already downhill, I'd expect maybe 64% of it to make it back. But it turns out only 7.8% is back. And then if I go on to experiment 2, actually experiment 3 was starting off with equal amounts of reactants and products. Experiment 3, we get a different percentage. And so we can't use the percent reaction to make a prediction. And so we start to look for other patterns. And so one of the things that we do is to graph it. And so if we graph it, we can take a look. We code these like magenta, blue, black, green. And so we start off with the reactants with blue and magenta, and the reactants are consumed. They're consumed in a stoichiometric ratio, so we're going to consume twice as much of the copper as we do the tin. And so that concentration is going to drop here. And then we're going to produce twice as much copper as tin here. And so we see this pattern. You know, once the reactions stop, we have no further reaction. This is called a dynamic equilibrium. Equilibrium means there's no change, so there's no change in the concentrations here. It's dynamic because things can go up and downhill. You know, there's motion. But once we hit the state of equilibrium, which is in the shadowed region here, there's no further change and the reaction essentially is over, even though it hasn't completely reacted. And so do you see a pattern there? Well, I see blue, black, magenta, green. Do you see the same pattern here once we hit equilibrium in the shaded region? Is it blue, black? Well, there's blue, black, magenta, green, but it seems to be inverted here. And then we go over here. Do you see blue, black? Well, here we have blue, black, magenta, green, but could you have predicted this? And so I don't see a pattern here. And so we might try to look for more complex patterns, maybe some mathematical pattern. Some of the patterns are quite complex, like number pattern. Do you remember the hydrogen atom spectrum from Chem 1A? In the hydrogen atom spectrum, let's draw this. Oops. We had a red, green, blue, and violet line. Do you guys remember that? And these lines can be characterized either by the energy, the wavelength, or the frequency. And it turns out there is a number pattern in this. We could do it by frequency or wavelength or energy. Rydberg did it by frequency, I think. But there are different forms of the Rydberg equation. Well, we had this mathematical relationship given by the Rydberg equation that allowed us to describe the lines in the H-atom spectrum mathematically. The Rydberg equation didn't talk about the theory. You know, this is what we call an empirical law. You know, the Rydberg equation is just some mathematical equation. We can punch in some numbers to get these wavelengths. But it doesn't tell us why, you know, why do we see just 4 lines and why are there these energies and this kind of stuff. It's just some mathematical description of this pattern. So that's what we're going to do here. We don't care what or how this pattern originates. We're just going to try to look for a pattern. Okay, so that's what we're going to do now. I'm going to just look for a pattern. So I'm going to copy this data and start from here. Unless, did we already start looking for a pattern? All right, these are our 3 experiments, and these are the equilibrium concentrations. You know, after the reaction stopped, this is where we stopped. In the molar concentrations here. And so let's first look at some patterns. And these are just kind of random guesses. So one of the guesses, there might be some kind of ratio. So let's go ahead and take the ratio of the products over the reactants. So I'm going to put the copper, the tin 4 up here, and then divide that by the copper 2 and the tin 2 down here. And let's see if there's a pattern here. So the first one, I'm going to just take 0.064 times 0.032. And then divide it by 0.036 and 0.068. And I get 0.8366 for the first one. The second one, we'll do 0.0433 divided by times 0.0717 divided by 0.0567 divided by 0.0283. 1.9348. Okay, let's do the last one. 0.1078 times 0.1039 divided by 0.0922 divided by 0.0961. I know, I must have made a mistake here. Let me try that again. Did somebody get it? Yeah. Well, I'm not going to call it Q. I'm just going to call it this ratio here. Yeah, 1264. 0. Not Q from the book. Q is a little bit different. I'm just going to try to find this. Is that a reproducible pattern? Do you see that? If you look at the numbers are quite different. And so this doesn't seem like a reproducible pattern here. And so what I'm going to do next is I'm going to use the coefficients here. So I have twice as much copper. So let's try this pattern. 2 times the copper plus times the tin 4 plus divided by 2 times the copper 2 plus divided by the tin 2. And so if I multiply the concentrations and double the ones with copper, what is the pattern I get? Well, it actually, the 2's cancel, and I end up with the same numbers. And so that doesn't seem to help anything here. And so I'll try different mathematical patterns, and eventually I might hit this one, or I'll take the copper plus and then square it. And then the tin 4 plus and not do anything. It's just raise the first power. So the coefficient I'm going to use to square it. Why would I do that? Why I'm doing that is because we're just looking for a pattern, and we don't necessarily know what it means. We're just looking for some mathematical pattern and just trying different things. So let's try this instead. So I'm going to have 0.064 and then square that times 0.032 divided by 0.036 squared divided by 0.068. And I end up with 1.487. Actually, I'm only allowed 3 sig figs, it looks like, or 2 sig figs. It's okay, we'll just extend it. All right, let's try the next one. The next one is 0.0433 squared times 0.0717 divided by 0.0567 squared divided by 0.0283. Shoot. Did someone calculate it? I need to bring my calculator in. Okay, 1.4775. Okay, can somebody do the last one? Does somebody have it?
1.4779.
How does this look? This looks pretty good because do you see they're all about, let's average this. The average is going to be about 1.48. We'll just go with 3 sig figs here. 1.48. And they're pretty tightly clustered. When we do averages, we look at a couple of things when we take an average. For example, we could average these too, but is this average going to be very meaningful if we average this? It's not going to be very meaningful because of the spread. Do you see how wide the spread is? That we can't have much confidence in this. Whereas this one has a tighter spread. Do you see that? Normally when we take averages, we assign something called a lambda 95 to that. And so what is a lambda 95? A lambda 95 is called a confidence interval. And it's called the 95% confidence interval. And so it's just a method in statistics. And what we do in statistics is we look at the number of measurements, 3. The more measurements, the better. So if we had 1,000 measurements, that's better than 3 measurements. But 3 measurements is worlds better than 2. And it's way, way better than 1. And the reason is because the more measurements we have, is we got to worry about error. We got to worry about 2 types of experimental error. The 2 types of experimental error that we worry about are systematic error and this is the second one. Both of them are kind of related to human, but or can be. But one of them, even if you get rid of the human element, is still present. That is, you cannot completely eliminate this error, random error. We cannot completely eliminate it, but we can get rid of it. The way we can get rid of it is if we take an infinite number of measurements. If we take an infinite number of measurements, then just based on probability, half of them will be an error too low, the other half will be an error too high, and eventually they'll just cancel one another out. But we can't take an infinite number of measurements, we can take a finite number of measurements. And if we take a finite number of measurements, then we cannot completely eliminate the random error. And then the other type of error is systematic. Systematic error we can completely eliminate because systematic error is due to things like calibration or making the same mistake over and over again. And so systematic would just be eliminated by improving technique or calibrating the instrument properly. Okay, assuming that we have no systematic error, then we can use some statistics. And using some statistics, since we aren't taking an infinite number of measurements, we have this lambda 95. And so the 95% confidence interval, which we can calculate, it's not too difficult of a calculation. It's going to tell us that based on statistics, we have a 95% chance that the true value lies within this range. But anyway, what we want to do is we want to do more. And so based on lots of measurements and lots of different reactions, this seems to be a consistent pattern. So we can take more, experiment 4, experiment 5, experiment 6, and see, do they come out to about 1.48 or not? we have this consistent pattern. And so in the scientific method, we start off with observations and we look for patterns. And if we get a strong pattern, a consistent pattern like this, then we call it a law. And this is going to be an empirical law. You know, there are two ways that laws are determined. One way is, let's go back to the scientific method. One way is empirically. So we start off with observations and we look for patterns. And if we can define the pattern in a simple mathematical expression, we call it law. And so this is empirical. Going this way. Based on that law, we can come up with some kind of hypothesis. Like, for example, one of the hypotheses would be, what is the origin of the square? You know, why are we squaring the concentrations? Does that make sense? You know, so we start to hypothesize these types of things, and eventually we end up with theory. And so this gives us the other way of determining a law, and that's based on theoretical approach. So in chapter 15, since we're cutting out here, I like to start off with an empirical approach first, just based on observations. And so this is what we're seeing here. The theoretical approach, this is going to be more from chapter 13. You know. And the law that we're going to generate is this. This is the consistent pattern that we see in these types of reactions. And that is, if we start off with the generic reaction, AA plus BB plus ... this is going to go to GG plus HH. These reactions are reversible, so we can have some mix of reactant and product, depending on which side is favored. It could be not an even mix, but a skewed mix. But the pattern that we see is that if we take the products raised to the coefficient power, so GG, HH divided by AA, BB, ... this is equal to a constant. In the previous case, that was 1.48, you know, based on our data set of 3 measurements. And we're going to call this constant K. K is called the equilibrium constant. In this case, this is Kc, because we're using concentrations here. We also have Kp. This is another consistent pattern. If we have gases, we could either express those in concentrations or we could express those in pressures. Pressure and concentration are proportional to each other for gases. And so we could have the partial pressure of G raised to the G power, partial pressure of H raised to the H ... over the partial pressure of A raised to the A, partial pressure of B raised to the B ... This is the equilibrium constant in terms of pressure. Or we might have a mix, you know. If we have a mix of states, then we have something called KEQ. KEQ deals, instead of with pressures and concentrations, deals with little a. So this is the generic equilibrium constant. Little a is called the activity. I asked you guys to review the activity, I think last week or the week before. Can somebody describe what the activity is? They're like 2 pages from the book. Have you had a chance to look at those? Oh, let me tell you again. I asked you to take a look at section 14.9. Which is about 2 pages of text, written text, maybe less. The activity is effective concentration or effective pressure. Well, what does that mean? Well, what that means is you can read this again. This is from Chem 1A. So review this stuff here. The activity. We don't actually calculate the activities. We just approximate the activities to simplify this. But anyway, this is the pattern. And so what we do is we test the pattern to make sure it holds. And it's been tested. It's been tested over lots of reactions, lots of experiments. And we see a consistent pattern here. So when we see that consistent pattern, we usually call it a law, but nobody calls this one the law. But essentially, this is the law of equilibrium, or the law of these types of reactions. So, equilibrium law. We don't have to understand the law to use it. This is a very powerful law because the equilibrium law, let me put that in quotation marks because nobody calls it the equilibrium law except for me maybe. But the equilibrium law is very powerful because this allows us to do stoichiometry. In Chem 1B stoichiometry, we ask ourselves something like this. You know, an example would be if we take acetic acid and allow that to hydrolyze water. When that happens, we're going to form hydronium and acetate. But we know that weak acids weakly hydrolyze. So we use K for acetic acid hydrolysis, which is going to be a different number. To calculate. So what we're going to do is this. We're not going to do acetic acid. We're just going to pick one of these earlier experiments and see, do we get the same numbers? So let's look at an example of Chem 1B stoichiometry. we'll go back to experiment 2. We already know what the answer is because somebody measured it via calculation. If we go back to experiment 2, it was 2 copper 2 plus a tin 2 plus. This is going to go to 2 copper 1 plus a tin 4 plus. And so we're going to use the K average that we got earlier. The average K value was 1.48. This is based on the earlier experiments. And then let's do trial 2. That is, we're going to start off with 0 molar here, 0 molar here, and then 0.100 molar here and 0.100 molar here. So we're going to start off with all products and then see how much makes it back. When you look at the K value, you know, it's a little greater than 1. A little greater than 1 means we have more product than reactant. And so it favors the product, but a little bit, you know, can make it back up because it's still fairly close to 1. And so we want to know how much makes it back up. And so over here, the amount of copper 2 is going to be plus 2x, where x, I don't know what it is, some variable. But I know if I'm going to form twice as much copper as I do tin. So tin is just going to get plus x molar. And that means I'm going to lose some of the copper, 1. So this is going to be minus 2x here, molar. And the tin, 4, I'm going to lose minus x molar, just based on the stoichiometric ratios. So at the end of this, at equilibrium, and this is what I want because at equilibrium, I know the K values. This is the law of equilibrium, whatever I want to call it. And this is going to be copper plus at equilibrium squared times tin 4 plus concentration divided by the copper 2 plus concentration squared divided by the tin 2 plus concentration to the first. And so I know that at equilibrium, that is, once this reaction has run its course, the equilibrium concentration of the copper 2 plus will be 0 plus 2x, it gives me 2x, and then for tin 2 it's going to be 0 plus x, that's just going to give me x molar. Over here for the copper plus concentration, I started off with 0.100 and now I'm going to lose minus 2x. I don't know what x is, that's what we have to figure out. And over here I'm going to have 0.100 minus x. And so in order to solve for x here, I need one more equation. And that is, it's going to be this. And that means the copper plus concentration at equilibrium is going to be 0.100 minus 2x. And then I square that. And the tin 4 plus concentration at equilibrium is going to be 0.100 minus x. So I'm just substituting these concentrations here into this equation. So I might be able to solve it. And this is going to be 2x squared, and then this is going to be x. So I'm going to ignore the units here for the K expression. And this whole thing has to equal 1.48. So when I look at this, this is going to be a cubic equation. Do you see it's third order? So I need to solve for x. do a little cleanup there. All right, this is still recording. So all I need to do is solve for x. If I solve for x, then I can figure out, what the change is. But there's a problem, and that is it's a third order equation. So how do you solve for x in a third order equation like this? One, you could get it into cubic form. That is ax cubed plus bx squared plus cx plus d equals 0. If you get it in cubic form like this, then you can use a calculator like this. This is my calculator that I'm using. I'm using the Castillo FX115 Plus. I have a black one. But this one solves up to third order equations. And so if I can get into that form, then I just plug in A, B, C, and D, and then it'll solve it for me. You can get a TI also. This is about $17 here. If you don't want to, that calculator is allowed, but a lot of you already have programmable calculators, and so you may not want to buy that. The non-programmable calculator equation solver only goes up to third order. So is there an alternative way to solve this? Yeah, have you guys solved these like cubic equations in algebra? You remember doing that? You can do it that way too. Was it easy to solve or hard to solve? You guys remember? Have you solved a fourth order or a fifth order or sixth order? We're going to have probably the most difficult one might be a sixth or seventh order polynomial equation like this. Can you solve that? Probably not. I can't. So let's say you don't want to buy this calculator. Is there another way to solve this? And there is. We're going to use the method of successive approximations. Method of successive approximations is discussed in Appendix A. So let's take a look at Appendix A in our book. And then try that out. So Appendix A goes through a math review, exponential, scientific notation, sig figs, multiplication, division, exponentials, logarithms. The quadratic. So if we have a second order equation, and you don't want to get that calculator, the Castillo FX115 can solve quadratics easily. You just have to get it in the quadratic form, which is up here, ax squared plus bx plus c. And then you just plunge in A, B, and C, and then it gives you the two x's. You can also use the quadratic formula. Here's the quadratic formula. So you don't need to buy the calculator, it just saves you time. We have a lot of second order equations that we solve in Chem 1B, so you either get very good at the quadratic equation or just get a bomb on those calculators. All right, then we have the method of successive approximations. The method of successive approximations is also called the guess and check method. So if you don't want to use the quadratic formula, you can do the guess and check method. Or sometimes the quadratic formula is a bit of a pain to solve. We can use that method. Etc. All right, I'm going to save some room here. So I'm going to solve for x, and then I'm going to go and calculate all these concentrations. So we want to know what this is. So I'm going to use the method of successive approximations. I don't have my Casio FX 115. I just have this. And I just have the basic calculator function on this. So we'll just do it that way. In the guess and check method, I'm not going to get this into cubic form. I'm just going to kind of leave it in this form, except I'm going to simplify it a little bit. And so I'm not going to multiply out the binomials. I'm just going to leave them. 0.100 minus 2x quantity squared times 0.100 minus x. The denominator I'll simplify because it's easy to simplify. This is just going to be 2 squared, which is 4. And then x squared times x is x cubed. So I get this equation, and this should equal 1.48. So what I'm going to do is I'm going to just guess the value of x, and then, but I want to take an educated guess. So we're going to guess the value of x, but it can't be any value because x can't go negative. And so the x should be between 0. It could equal 0. Maybe there's no change. Well, actually, that's not really possible considering the ratio here, but x should be greater than 0, but it should be less than 0.05. Now, how did I get the upper limit on x there, 0.05? Because if x is greater than 0.05, then that's a problem. If x is greater than 0.05, I'm going to get a negative concentration. As the concentration here I have for copper 2 is okay if it's greater than 0.05, but the concentration of copper plus here won't be okay because 0.05 times 2 is 0.1. 0.1 minus 0.1 is 0. 0 is the lowest concentration I can get. So if I had greater than 0.05, then I'm going to get a negative concentration here. And a negative concentration is not possible. And so 0 is the lowest. All right, then it's going to be an educated guess. The ratio is 148. If the ratio were 1, then it should be even, 50-50. But the ratio is slightly biased towards product, since it's greater than 1. And so that means it should be less than 0.05, that goes. And so let's go ahead and take a guess. What do you want to guess is your first x? Let's just go with one digit. If we go with one digit, there's less punching in the calculator. And so 0.03. 0.03, okay, try that. And so if x equals 0.03, then what do I get for this expression here? K is going to equal, and so just plug it in. Two times 0.03 is 0.06. 0.1 minus 0.06 is 0.04. So I'm going to do 0.04 squared. You guys can punch this in too, in case I make a mistake. 0.04 squared. All right, 0.1 minus 0.03 is 0.07. So times 0.07 divided by 4 divided by 0.03 squared. 1.633. It's a little bit high. Our target is 1.48. So how should we change K? Should we make K bigger or smaller? We want this number to be smaller. Should I make K small? X smaller or bigger? Bigger? All right, we'll go bigger. We're going to try 0.04. All right, 0.1 minus 0.04 is 0.06. So 0.06 squared times wait, I got it wrong. Sorry. 0.04 times 2 is 0.08. So that's going to be 0.02 squared times 0.06 divided by 4 divided by 0.04 squared, cubed. Cubed. Does somebody have it? This is low. Seems to... Did I get that right? What did you calculate, Tristan? That's what you got? All right, what should our next guess be? What?
Something in between.
Something in between? Closer to 0.03 or closer to 0.04?
Closer to 0.03.
All right, so let's try 0.03 what? 1? Okay, let's try 0.031. All right, let me try this with this calculator. 0.031 times 2 equals minus 0.1. I'm going to square that whole thing. Times, okay, 0.1 minus 0.031 would be 0.069. 0.069 divided by 4 divided by 0.031 cubed. Am I getting warmer or am I getting colder or what?
Oh, sorry.
Warmer, yeah. Seems to be getting warmer. Is that what you got? All right, so what should we do next? It looks like it's between 30 and 31, maybe? Closer to 30. So 0.030. 5 would be halfway between. 2. 302. Let's try that and see what we end up with. So I'm going to go 0.0302 times 2 minus 0.1 equals square that whole thing times 0.1 minus 0.0302 would be 0.0698 divided by 4 divided by 0.0302 cubed. What did you get? .9934. Let me all right, what do you want to do next? Let me double check the 0.03 one more time here. 0.03 times 2. Maybe that's okay. Let me just do something here. It looks like we're getting closer, right? But let me just do a quick side calculation here. What if x is equal to 0.02? What would my k be? I just want to see how it's ramping up and how far to go, what the trend is here. So I'm going to go with 0.02 times 2 is 0.04. It gives us with 0.06 squared times 0.08 divided by 4 divided by 0.02 cubed. I get a k value of 9. Mm-hmm. Let me just double check this other calculation really quick. Yeah. What did you get?
1.037.
1.037 for what? 0.03?
Yeah.
Okay. Yeah, something was weird with the number. So 1.037. All right, thank you. What did you get for 0.02? Did you get 9?
Yeah.
All right, so it looks like it's between 2 and 3. Uh-huh.
I think we got it.
You got it?
Yeah.
Okay, what did you get?
I got 0.02833.
So you went to x equals, well, actually, you got it right. But the next step would be this. This is 9 This is 1.03, so it's closer. It's between 2 and 3, but closer to 3. So 0.028 is closer to 3, right? So you did that?
Yeah, because I was way too high.
Okay, then you go, okay, it's going to be between 20 and 29 next, right? What did you get for 0.028? Did you write it down?
I did.
All right. And then you probably went to 0.029. And then you went to 0.0283. And then it still didn't quite round off. And so then you went to 0.02833. Is that what you did? Pretty much? All right.
I was guessing.
And so you just guess and check, and eventually you get this, and it comes out to 1.480. Is that what you got? Okay. The goal is it must round to 1.48. That's our goal. Uh-huh.
Put in the calculator, you just do the key, you don't have to go through the guessing tool.
If you
have the equation solver.
Yeah, right. If you have the equation solver, but the pain about the equation solver is you have to get it into cubic form. And so you have to spend some time rearranging it algebraically from this to this. And so it's not so easy.
Can you show me how you got the range again? 0 is less than 2x.
Well, these concentrations have to be positive. And so x can be any positive number here. We can't have x as a negative number.
Yeah.
But over here, I have 0.1 minus 2x. And so I can't let this go negative. So if x were 0, it'd stay positive. And so what is the biggest x value I can have that will keep this number positive? And so that would be 0.1 minus 0.1. And so x has to be half of 0.1, which would be 0.05. Do you see that?
Oh, yeah.
And so x cannot be greater than 0.05, because if it goes bigger than 0.05, then this is going to be more than 0.1, and it's going to go negative. And concentration can't go negative.
Yeah.
It's like if somebody asks you, I'm on a diet, I want like negative 10 calories, for lunch. Can you have negative 10 calories for lunch?
No, you can have 0.
Yeah, you can have 0, but you can't have negative 10. And so that's fine. And so basically what we're going to do is we just keep grinding this out. And so we calculate, are we getting warmer or colder? Warmer or colder? Warmer or colder? None of these round to 1.48 until we hit this one. And then this one rounds to 1.48. So to make a long story short, somebody just went ahead and did this for us. But we do it. We just slowly narrow it down. And so we have 0.02833. And so we go back up here and plug those in. So x, this is 0.0283. I'll just go with 3 sig figs, but I'm going to carry an extra. So I'm going to say 2833 with the last 3 subscripted. And then double that for the copper concentration. And so we'll take 0.02833 times 2. .0566. And then I'm going to do these subtractions here. I'm going to get 0.1 minus 0.0566. Triple six, and this is 0.043. Actually, I'm going to go 3 decimal places here, so I'll subscript the last 2 digits, 34. smaller. And then I'll go 0.1 minus 0.02833. So these are the equilibrium concentrations here, based on calculation using the equilibrium law. There's a way to double check our calculation. The double check involves plugging it into K and seeing if I get the right ratio. So I'll go ahead and take the concentration of the products, 0.04334. This is why I carry extra digits, so I can avoid round off error. I'm going to square that times 0.07167 divided by 0.05666 squared divided by 0.02833. So this should come out to 1.48 or close to it. So let's see, 0.04334 squared times 0.07167 divided by 0.05666 squared divided by 0.02833. And this comes out to 1.4801. So it checks out to match. All right, so we can compare this with the experiment, and the experiment should have given us the same value. This was experiment number 2. So from experiment, they measured 0.0567 for the copper 2 at equilibrium, 0.0283 for the tin 2 at equilibrium, 0.0433 copper 1, and 0.0717 tin 4. Do you see that? We didn't have to measure this. We were able to calculate the equilibrium concentrations based on the equilibrium law. And so this is very powerful. What we want to know what K is for all our reactions. So for Chem 1B stoichiometry, we need the K value. The equilibrium constant. So what are the ways to determine the equilibrium constant? One way of determining the equilibrium constant is by observations, that is, experiments. I'll just call it experimental observations. In other words, we'll just measure the equilibrium concentration. All right, I lost some of that. Let's take a break right now while I try to sort this. Um, take like a 15-minute break or something.